join us this afternoon. About 40 years ago, Harvard Magazine asked one of that university's young faculty members to write an article about a highly popular course he was regularly teaching. At one of the most famous research universities, hundreds of students were choosing a course in which evidence from disciplines across the liberal arts and sciences was being integrated to present an account of the stages across which an arrow of time flew from the Big Bang to ourselves. Eric Chaisson explained to this magazine's readers, as he did to his own students, how we are part of a rapidly expanding universe and a most recent step in a 14 billion year journey. He showed how Copernicus, Hubble, and others revolutionized how we saw ourselves in space. He presented evidence for the more recent revolution and how we see ourselves in time. He integrated his own work with that of many others who had translated the chapters that were first told by light, rocks, bones, and blood. Professor Chaisson puts these accounts together in an epic of evolution that clarified important challenges that we are facing today and responded to a search for a big picture worldview that his persistently curious students were then seeking, that he was too, and that we all still are. He and the students were not the only ones who were seeking to know who we are and whence we came. The Harvard Magazine article won the Smith-Weld Literary Prize for the best general article by a Harvard faculty member that year. It also garnered 6 unsolicited book contracts, one of which, with the Atlantic Monthly Little Brown, led to Professor Chaisson's first book, Cosmic Dawn, which won several more literary awards, and much grief from his colleagues who thought he was misallocating his time and effort by integrating knowledge from many disciplines to tell the great evidence-based epic of our time. So what brings a senior, tenured member of the Harvard faculty who has waived any honorarium to be with us today? Maybe because throughout his career, he has cared passionately about developing better and better approximations of reality, about how what his own discipline has demonstrated can be integrated with what other disciplines have as well. He cared about great questions that he shared with his students, readers at his universities, and communities even beyond academia. And after 40 years, he still is teaching the cosmic evolutionary effort, albeit now with what he finds to be richer insights and even more supported data. So his love of sharing all of this is what brings Professor Chaisson here today. So if you would, please join the Villanova Institute of Teaching and Learning and its special grant for interdisciplinary teaching and learning, the Villanova Center for Liberal Education, the Departments of Astrophysics and Planetary Sciences, the Departments of History, Physics, the Institute for Global Interdisciplinary Studies, and the Honors Program in welcoming Professor Eric Chaisson to Villanova University.
Well, thank you, Lowell. Thank you very much for that kind introduction, and thanks very much for inviting me to Villanova. I remember you first tendered this invitation, I think it was at breakfast in Moscow, about 3 years ago. Yeah. And you've been asking ever since, and I'm glad and gratified that you kept asking because it really is a pleasure to be here. Well, I want to share with you an incident that occurred in a setting like this, must be 20 years ago now, at another university well to the south of here. I was speaking about a similar topic. Evolution was in the title, and I always get a little worried when, of course, I'm well below the Mason-Dixon line with that particular topic. And yet this was a very respectful group. They were very interested, huge auditorium. And with the exception of one gentleman way at the back, I could see him, he was upset about something in the last row, early into my talk. And another few minutes, he was up, out of his seat. He was oscillating back and forth, causing quite a disturbance, less for me than for the people around him. And within 5 minutes thereafter, I had hardly begun my talk, really. I don't think I had even mentioned the word evolution by that point. He was waving a book and yelling at me. And he was saying, "Is this book fiction?" Well, he was escorted out of the room pretty quickly. But of course, it was very intriguing to me to find out what was the book he was waving. I found out thereafter, relatively quickly, it was The Phenomenon of Man by Teilhard de Chardin, a paleontologist who was also a Jesuit. I had never heard of Teilhard at that moment, 20, maybe it was 30 years ago, I'm not sure now. But when I flew back to Logan, I went directly to the Harvard Coop and bought the book. I took it home, I read it, I finished it, I looked out the window, and I said to myself, is this book fiction? Very much the same. It's, you know better than I, Taha Desjardins. One of those guys I wish I had had the opportunity to meet. A person nonetheless who mixed his science with his mysticism. He was in trouble both with the scientific community for bringing religion into science, as well as in trouble with the church. In fact, was exiled for many years, I gather, to China, because he was stressing the role that evolution, Darwinian evolution, had rendered humankind. But he was also a mystic in the sense that he thought the evolutionary story, about which I speak a little bit today, culminated in humankind. That we are special, that we are unique, that we are the pinnacle and culmination of the evolutionary story, made, I guess, in the image of God. There are many ways to address the topic that I'm going to talk about today. There are many ways to try to understand who we are and where we came from, and how we can gain a sense of place in the cosmos. There's art, and there's music, and there's literature, including poetry. There's, of course, history, big history. There's philosophy and theology, and there's also science, natural science. I'm a natural scientist. I respect people like Taha Desjardins, whom I, of course, never met, but you respect him too, if only because he received, despite his controversial calling, I suppose, he received here on this campus in 1937 the Mendel Medal. I mean, how many times do the Augustinians give a medal to a Jesuit? I mean, that's pretty rare, I suppose. But I am a scientist, and as a result, the thing I believe in the most is the scientific method. I believe that ideas and beliefs need to be tested. That's simply my genetic flaw, I suppose. I believe strongly that empirical data, quantification, observations, experiments in the lab, controlled conditions, empirical information will be the way that we can discriminate between what the sense and the nonsense, and thereby gaining and accumulating more and more of the sense and discarding the nonsense. We will gain not a measure of truth, wouldn't know how to define it, wouldn't know it if I fell over it, but as Lowell mentions, a better and better approximation of reality. I like that phrase. I think you were plagiarizing me in the introduction. So I'm an experimental physicist by training. I'm an astrophysicist by vocation, and I'm an empirical materialist by philosophical bent. Not a dialectical materialist, as we stressed in Moscow. An empirical materialist. I sense strongly that neither believing alone nor thinking alone will ever make the unknown known. You've got to test something. You've got to look out the window. You've got to observe. You've got to be critical. On this campus, perhaps in some of the language of your language here, I'm the doubting Thomas. I'm the skeptic. Show me. Show me the data. Because I think that's the only way we'll be able to cut through some of the reality, not necessarily the truth, but a better and better approximation of what's real and who we are and whence we came and how we fit into the larger scheme of things. In effect, how we fit into how we can gain a sense of place. So I'm an astrophysicist for the most part during the day. And it's a very exciting time to be an astrophysicist. I would imagine when the historians of the future, 300, 400, 500 years from now, write the books about us, they're likely to conclude that we are now living in a golden age of astrophysics. And I say this because the number of discoveries and the frequency of discoveries being made in astronomy and astrophysics are, well, they're astronomical. I mean, it's really an exciting time to be an astrophysicist. I say this largely because we're opening up the entire electromagnetic spectrum in a single generation. Not the generation of my parents and not the generation of my kids, but the generation of the astronomers and astrophysicists who are now working, are opening up and sensing the entire electromagnetic spectrum and seeing the universe in all of its available wavelengths. But by the same token, I think that when the historians write the books in their future about us, they'll likely conclude that we are now also living in a golden age of biochemistry. Because I think the advances and the discoveries being made in the biomedical community, despite some of the controversy over the past few years about reproducibility, is equally as impressive and equally as fantastic as those of us working in astrophysics. In fact, I wish I had been a biochemist, I confess. Although it's interesting, the other day, a few weeks ago at a dinner at the faculty club at MIT, I ended up sitting beside a Nobel Prize-winning biologist, a biochemist in fact, and after a few drinks, maybe more than a few, he wished he had been an astrophysicist. So maybe there's always this feeling that the grass is greener in the other guy's yard. So I mentioned these two subjects, these two interdisciplinary subjects, astrophysics and biochemistry, because I've been fortunate to be able to work in each of these areas, and also fortunate to be able to explore the extent to which we can bring these two already interdisciplines together into a grander interdiscipline, something that you might say like akin to a transdiscipline. And that is what I call cosmic evolution. Now you can put me in the corner and say, what do you mean by cosmic evolution? What's the definition? I would say simply change through time. If you say a little bit more information, please, I would say something like the definition there. Hopefully you can read this as high res as we can possibly project through that projector. Cosmic evolution is the grand synthesis of many developmental and generational changes in the assembly and composition of radiation, matter, and life throughout the entire history of the universe. The emphasis is on change. I'm not the first to emphasize that. You know, Heraclitus looked out his window 25 centuries ago and said, Pantore, Greek, for all fluxes, all flows, nothing stays the same. We now say apocryphally, I think, that he said, there is nothing permanent except change. I don't think he really said that. But you get the gist of it. Change is universal. Change is ubiquitous. So there's universal change that I see out my window. I give a sexy name, cosmic evolution. Some of the change, of course, is slow and subtle. Other of the change is more dramatic. For example, when the sun when the sun changes, each and every day goes through its evolutionary paces. It's fusing hydrogen into helium within its core. Yet there it comes up. You're going to wash out my slides. Why are you doing that? Huh? No. Why? I would rather not have any light on the slides because the resolution of the slides is poor. And so I'm trying to make this area all through the stage area dark as possible so that the slides can be seen better. Why do you want to increase the luminosity there?
Because we can't see it.
Huh? No, see, that's too dark. No.
How about that?
That's where we were, I think.
Yeah.
That's the third setting from the top.
Yeah.
That's where we were. That's where we were.
Backlighting helps. So.
Okay. All right. Change. Some of the change is subtle and gradual, such as, again, when the sun burns or confuses ever so slowly. But other of the, and of course, the plates drift across the surface of the Earth at the rate at which our fingernails grow. But other of the change is more dramatic when stars that are more massive than our sun explode as supernovae rather dramatically, or when the plates suddenly quake and dislodge to the tune of 11 o'clock news reports of earthquakes and volcanoes. But it doesn't matter to me whether the change is subtle and gradual or whether it's dramatic and sudden. I see change. I defy you to show me something out the window that's not changing, provided you look long enough. A couple of caveats before we proceed, just so you know where I'm going in advance. When I say cosmic evolution, let me put the emphasis differently. When I say cosmic evolution, I'm not talking today just about astronomical systems. stars and galaxies, planets and the like. I'm using the word cosmic in the larger universal sense. I'm talking about evolution on all scales, writ large, broadly conceived. I'm talking about changes among big and small, late, near and far, past and future. Consequently, the kind of evolution we're most familiar with, that we all learned in school, neo-Darwinism, becomes just one, albeit very important, subset of a much grander scheme proposed for evolution. Second caveat, when I say cosmic evolution, I'm not trying to take today the essence of neo-Darwinism, notably the principle of natural selection, and extend it on into the universe. I'm trying to do more than that. I'm trying to explore whether there might be a principle, a mechanism, a process, a law, which would guide the evolution and change of all systems, all complex systems, whether those systems be galaxies, stars, planets, life, society, or now machines. So I'm trying to explore the extent to which there might be something akin to a principle of cosmic selection. And among life forms on other worlds, should there be any life forms in other worlds, it might simply be that advanced life forms that can get their act together well enough, quickly enough, will survive karma, and those that don't, won't. I mean, we're kind of at the cusp of that now as a civilization on Earth. A little bit more about that in maybe 22 and a half minutes, and then more, you can drive the discussion later about our ultimate fate, perhaps. So with cosmic evolution, frankly, I'm trying to look at this subject, this grand subject, this transdisciplinary subject, which is a merger of interdisciplines, astrophysics and biochemistry in the main. And I'm trying to view this as a cosmic heritage. It's a cosmic heritage because this story, it's a narrative, it's a scientific narrative. It's coming to us out of the past. We're looking out the window and we see everything delayed. The farther away it is, the more it's delayed. I even see you delayed by nanoseconds. The galaxies by many years. It's a heritage not only because it's a structure that's coming to us from the past, but it's a blueprint that we can grasp in the present, and maybe it's a roadmap that we can take on with us, or at least our descendants might take with them on into the future if they are to have a future. Because I think perhaps the next great evolutionary leap forward in the scheme I suggest for you today might be something akin to ethical evolution. More on that later, maybe. I don't know. I make this stuff up as I go along. And namely, I look at your eyes and I edit, clock your eyes, etc. In effect, although it sounds very grandiose and a little arrogant, maybe a lot arrogant coming from Cambridge, I'm trying to explore whether the time is ripe to try to build a new philosophy. A philosophy for today's world, a philosophy that is really a scientific philosophy. It's a philosophy because we want to ask the same fundamental questions that the great philosophers and theologians have always asked, but we now want to bring the power, and I think it is a power, of technology and of the scientific method to bear upon those questions, to discriminate between the sense and the nonsense, and to gain better and better approximations of reality. What are the questions? Well, you know them as well as I. Probably know them better than I. I mean, basically, from a scientific point of view, who really are we? Where have we come from? Where has everything around us come from? Look out the window. The air, the sea, the land, the planet, the points of light in the nighttime sky. What is the origin of all that stuff? How is it that when I look at systems, among them in the main, galaxies, stars, planets, life, society, not only are there ordered structures that have structure and function, but that over the course of time, it seems as though those systems have increased in complexity. We have this general feeling that over the course of time, things have become increasingly more complex. Yet the second law of thermodynamics, which plays a big role in the subject, is the entropy law. And that's the law that suggests things ought to be, in the main, breaking down. I look out the window and I see certain systems are increasing in complexity. Yet the most cherished law in all of physics, after all the other laws of physics of Einstein and the rest are probably shown to be incorrect, we have this gut feeling in physics, at least I do among my colleagues, that the second law will survive. The law of entropy, the law of disorder. Can we reconcile, therefore, the increasing complexity and order of structures, such as galaxies, stars, planets, and life forms, with the theoretical insistence of the second law of thermodynamics, that things ought to be, prima facie, breaking down? I think the answer is yes. We come to see, and you'll hear me say this a number of times, I think, today, depending on how I edit things, that these systems, again, one more time, galaxies, stars, planets, life forms, society, machines, are but islands of complexity in seas of great disorder. Both order can increase locally and disorder can increase globally, and all is in accord and can be shown to be in accord quantitatively with the second law of thermodynamics. So we have this arrow of time. I've used this arrow forever, for my whole career, really, as a graphic. It's just a piece of art. I happen to be married to an artist, and she does my art for me, for the most part. And I show in this graphic the entire sweep across the history of the universe. From at the left, the Big Bang, to the right, the present time. Again, the left, Big Bang, 14 billion years ago, to roughly the present time here. There are a number of assumptions about time. You can even ask me, before I even show you what the assumptions are, you can ask me, what is time? And you know, your intellectual forebear, Augustine, spoke about this in City of God, 5th century, and said basically what I say now, namely time is pretty obvious until you try to define it. Einstein taught us that in the 20th century that time is the fourth dimension. Psychologists tell me that time is a way of distinguishing or discriminating between past and future by way of the present. I prefer Henry David Thoreau's view of time as a stream I go a-fishing in. That's pretty much on my page. But there are assumptions, and one of the assumptions in making this model of cosmic evolution that I share with you briefly today is that time moves linearly. Time doesn't reverse. Time doesn't go backwards. Time doesn't speed up and slow down. That is an assumption. I'm not saying that it's true. I don't know what is true. We'll never know what is true. I always look at Lowell when I talk about truth. We had that battle in Moscow. But assuming that time is running linearly is a little akin to saying, well, it's a little like 2 and 2 = 4 everywhere. It's a little like saying that hydrogen atoms are built the same at the limits of the observable universe as they are built in my lab. If those assumptions aren't right, then it's hard for me to proceed. There are about 7 major construction phases across here, not making any allusions to any other great poetic expressions of basic truths. I just see 7 major construction phases. From the early times when the earliest of atoms became somehow the galaxies evolved or changed to create the environmental conditions for the growth of stars, the emergence of stars. Stars created the heavy elements within them, some of which exploded outward to become heavy or rocky planets. Rocky planets gave rise to the environment suitable for the origins of life, chemical evolution that preceded biological evolution, and onward toward the culture and technology that we now share. There seems to be a thread of change associating the early universe with the present. A thread of change that moves the universe among those islands of ordered systems from one that was fully disordered, to one that has some order, from inorganic to organic, from chaos to, well, order again, I guess, I suppose. The thread of change that moves across here. But again, this subject requires us to recognize, should it be a reasonable approximation of reality, that the kind of evolution that we know and like and know much about, neo-Darwinism, is just one subset, albeit a very important one, across this entire evolutionary scheme. This graphic, by the way, is part of a massive website that I've built over the years. It's free and open access to anyone. There are no firewalls. It's very, very large. It's multimedia. It's the essence of the course I teach back in Cambridge. And it has, these are all hot when you go online. It goes deeper and deeper and deeper. But in addition, it has not only an introductory track, which is the track I use in my class of science for non-scientists mainly, but also has an advanced track for those of you who are in the sciences who may want to examine some of these various epochs all along the arrow of time. And they may be suitable for upper level, undergraduate, even graduate studies. It's all free. Just Google Cosmic Evolution, Harvard. It just pops right up. So a couple of background pieces of information very quickly concerning how we base the story on cosmological science. Here's one of the strongest pillars of modern cosmology, namely the study of distant galaxies. This is a Hubble photo in the background, superposed on it these numbers from the Keck telescope in Hawaii, showing various galaxies that can be measured in terms of their red shifts and therefore interpreted as objects that are moving away from us by a certain rate. This leads to the so-called famous Hubble law, which shouldn't really be called that. Hubble gets a lot of credit, in my opinion, for work that he shouldn't really be credited for. In 1929, Hubble published a paper in which some of these earlier measurements suggested an expanding universe because of all the galaxies receding away from us. Not clear historically whether Hubble himself, the man, actually bought into the recession of the galaxies as indicating an expanding universe. But it is pretty clear that he didn't do most of the work. Most of the work was done by his assistant, Humason. Milton Humason began at Caltech as a janitor and did such a good job picking up the trash. He was made a mule team driver. Those were the guys who took up every afternoon the unexposed plates to the top of the mountain at the telescope, and then at dawn brought the exposed plates very carefully on the mules back down to Pasadena. And he did such a good job at that, he became telescope operator, and then before you knew it, Humason was Hubble's valued assistant. And in many ways, I spend much more time on this in my class. I like to call Hubble's law the Hubble-Humason law. But even before that, the whole idea of the Big Bang cosmology was proposed by another person who was wearing a collar, Georges Lemaitre. Georges Lemaitre is really the father of the Big Bang, in the opinion of many of us. Years before Hubble began to see the recession of the galaxy and even suggested it might have something to do with Big Bang cosmology, Lemaitre proposed that there was a Big Bang. He didn't call it that. They called it an original yelm of some sort. And he should be in many ways, I think, credited with the theoretical underpinning of the Big Bang. He also came here to Villanova a few years before Teilhard de Chardin came, also Lemaitre, to receive the Mendel Medal from the Augustinians. He was not a Jesuit, though. There's another piece of information that goes along with the recession of the galaxies, which is the cosmic microwave background, just presented in this oval projection here of the radiation that comes to us from the early epochs of the universe, kind of the oldest fossil. It gets picked up routinely now over the last several decades by radio telescopes on the ground and in orbit. and provides a second pillar, a second of three pillars. I'll only mention these two, that provides very strong evidence that the universe was once denser and hotter and has now thinned and cooled. We're always on the lookout. I was having lunch just yesterday with one of the discoverers of this, Bob Wilson, up in Cambridge, and we were chuckling about how over the last couple of years there have been somewhat, I guess you'd call them mysterious signals being picked up by one of the big telescopes in the outback of Australia at Parkes radio telescope. And you're always on the lookout for serendipitous observations like this, pieces of data that are coming into your observational equipment, because this, in fact, discovery itself of the 3-degree cosmic microwave background was found rather accidentally decades ago. We now know, as of last July or so, that the mysterious signals coming into the Parkes antenna for the last few years was actually caused by a technician in the basement of the telescope who was opening up the microwave oven just a little bit too quickly when he was trying to zap his tea. He was opening the door of the microwave oven quickly before it dinged, and the telescope would be zapped. And so that's, well, it's a good experiment, but no good cosmological information there. So I can turn these pieces of information here into a graph. And it's a graph that you can understand, although initially it looks just a wee bit technical. And it graphs just two things, density and temperature. I tell my kids, my students, that if you're in the backyard, for example, and you have something that's odd, you've just picked it up, and you're trying to figure out what the hell it is, try to get its temperature and try to get its density. From a thermodynamics point of view, if you can understand both the temperature and the density of that odd thing, you can learn a lot about that thing. In this case, this plot, based on these data, just plot here two things, the density and the temperature. Here comes the temperature. The universe is cooling from its earliest epochs to the present. Here comes the density. The universe is thinning. Because the universe is expanding, the universe is both lowering its temperature and lowering its density. And over the course of time, although be careful, I'm not running time in this particular case linearly, I'm running it logarithmically, in order to emphasize some of the more interesting aspects of the earliest universe, when there was no complexity, when there was no order. That's because when the temperature was very, very high, and the density was extremely high, higher than anything associated with anything on Earth or even anything in the interiors of the sun, stars, the universe was so chaotic and so disordered that even if a proton, a fancy word for which is hadron, tried to come together with a lepton, which is another $50 word for electron, then the radiation was so seriously strong in the earliest epochs of the universe that proton and electron would not be able to combine even into the simplest atom called hydrogen. But eventually, as the universe had cooled and thinned, now non-linearly, see here's the 0th point of time, here's 1 second of time, here's 1 year, here's a million years, here's 10 billion years, roughly 14 billion years. In this vicinity here, sometime between the first few minutes and the first million years, which sounds like very inaccurate observation, but it's really a statistical argument that gives rise to this period in through here that I've got labeled atoms, being the time when finally the universe had thinned and cooled enough to allow some of those protons to merge with electrons to make the oldest ancestor, the oldest fossil, which are hydrogen atoms, which are now, of course, the most dominant and abundant elements around. And then eventually, over the course of time, somehow, to continue that story, those atoms became galaxies, galaxies spawned stars, etc. There's a lot of information in this slide. I certainly don't go over here, of course, not even in my class. Augustine, again, to mention one of your heroes. Augustine was over here, and again in the 5th century, City of God. And the way I read it originally, he was talking about, in effect, we would now interpret that to be before the Big Bang, hell was being created for people like us who were about that issue. But Hawking told me once, to the extent that I can understand through the box, that Augustine really didn't say that, or at least he didn't say that he thought that in 5th century. Augustine was simply at the time suggesting what people thought popularly in the sense of the Big Bang, in effect what we now call the Big Bang of the origin of the universe being preceded by the notion of hell. So now I present for you just a gutsy plot that runs over this same time sequence from the earliest epochs of the universe to the present, now. And this shows system complexity, whatever that is. In fact, maybe I should throw up a definition. Occasionally these are useful. Complexity is a state of intricacy, complication, variety, or involvement as in interconnected parts of a system's structure and function. This is the gut feeling we have, I have anyway, many other people concur, that as we look out the window we see among various systems, galaxies, stars, planets, life, society, that these systems are somehow increasing over the course of time. Now, of course, complexity can also be noted in terms of other synonyms: order, information, entropy, organization, the whole long list of these things. I'm just talking about, again, the degree to which a system is structured and functioned by way of kind. And noting that over the course of this graph, which is just a gutsy feeling, that there are 3 basically different kinds of systems. There are physical systems, there are biological systems, there are cultural systems. Generally, in the earlier universe, there emerged physical systems. This is a globular cluster. I think it's M80. It's about 100 light years across, beehive collection. It's not that complicated, though it's becoming more complicated than we thought a few years ago, perhaps. A globular cluster is a relatively simple system because it's a physical system formed in the earlier universe compared to a life form. Well, this is a graphical representation of molecules distributed along a DNA axis. So the scale is wildly different. This is light years across, tens of light years across, associated with a physical system that may have formed in the earlier universe. This is nanometers across, down the DNA molecule. The colors are such that, let's see, looking at it, red is oxygen, green is carbon, blue is nitrogen, yellow is phosphorus, and hydrogen would not be shown there. And then I compare this biological system, which looks a little more complicated, with this cultural system, which I've chosen here, maybe because of the audience I'm addressing, to be the rose window at the Notre Dame Cathedral in Paris. Something that nature, without sentient beings, technological beings, would not have built on its own. This system here is notably more complicated in many ways than nature would have built. And here's another way of letting my wife, Lola, artist, go to work on these various systems to try to emphasize for you again that the universe was moving from one that was filled with radiation, that because it was thinning and cooling and expanding out into larger volumes, giving rise to matter, clumps of matter, and eventually to life. You see there's some artistic license built into this as well. It's another graphical representation of the arrow of time. But in this case, it makes clear the arrow of time is not pointing at us. There's no directionality necessarily. It's not converging. This is an arrow representation which I like because it's diverging outward. You can see if you look at some of the details there, she used some considerable artistic license on the end over here when she's reached cultural systems. So I ask you to consider now these 3 systems: physical systems, biological systems, and cultural systems in this remarkable photograph. I asked an astronaut to get a photograph like this for me on orbit, so it's a little contrived, but the idea was to get a single photo which shows each of those 3 systems. And so we see in this photo a physical system, let's say the sun. The Earth is also here, but let's just look at the sun. The sun has a flow of energy through it. It has a certain amount of waste, in effect, moving out of it. There's a definite movement of energy through that system, and it's not terribly complicated. There's a biological system in the suit here. That's Kathy. She's looking at her menu because she knew I was going to talk about her eating a certain amount of food per day. As humans, we eat about 2,800 kilocalories per day. It's equivalent to about 120 watts of food we eat per day, typically on average for an adult, mature. And then there is, thirdly, in addition to the physical system, the biological system, the cultural system, namely the device that brought her there, the shuttle, that also requires a certain amount of energy for its operation. Each of these systems, whether they be physical, the sun, biological, the astronaut, or cultural, the device that brought her there, can be examined from a thermodynamic point of view as a box. Not a spherical cow, but a box. And this box is open. It's open because each of these systems have energy moving through them from the outside environment. In fact, that's the key, I think, to many of these complex adaptive systems. They must be out of equilibrium. They must be open to energy moving in and waste moving out. And they must be able to acquire, store, and express energy while they maintain their structure and go about their function. We just analyze it in the following way. Here the box is open. Energy, E, is moving in. She's eating a certain amount of kilocalories per day. Q, that's the waste. Heat, in particular, is moving out. And the entropy is growing at certain rates. Actually, the entropy can be shown for some of these systems, such as galaxies, stars, planets, life, and society, to be decreasing temporarily within the box. Kathy's structure in her body, she's maintaining her body's structural integrity for, on average, 70 years in the West. The star lives longer. They endure as long as energy is moving through them. They die once they stop. If the sun were to stop fusing, it would collapse. If Kathy were to stop eating, she would die. If the shuttle didn't have power, it wouldn't, well, it's not flying anyway now. That's politics. But I'm trying to compare and contrast these basically three kinds of complex adaptive systems: physical, biological, and cultural systems that seem to have associated with them at face value an increasing amount of complexity associated with the amount of energy flowing through them and or the amount of information I need to describe each of these systems. So we're starting to talk a little bit more now about life, biological systems, not just stars and galaxies. And of course, once you start thinking about life or talking about life, initially there might be the feeling that, oh, he's turning the page and he's going somewhere else now. Life is different. I don't think it is different. I think there's a continuum of complexity from these earlier systems, such as we describe as stars and galaxies, all the way up through living forms, all the way up through cultured forms as well. Life is no different in kind than a star or a galaxy. It is different in degree, different in degree of complexity. Life of all forms is more complex than anything I see on the sky. Even the smallest amoeba in my backyard stream is more complex than anything I see on the sky. You know, I could make an attempt to define life, since I'm throwing up a few definitions periodically. It's a challenge to define life. I mean, by contrast, I can go anywhere in the world as a physicist and ask any physicist who's been trained anywhere and who has any personal persuasion, what is matter? And he or she has the same answer. Matter is anything has mass and takes up space. But if I have 10 or 12 or 100 biologists in a room and I ask them what is life, I'm likely to come up with a lot of different answers. When I first began teaching this course, I wanted to get a definition for life going, because I was trying to be careful as I proceeded along by offering students certain definitions over the course of the course. And so I went actually to the biology department where there were a whole stack of Nobel laureates all lined up, and I asked them one after another, what is life? And some of them hadn't thought about a definition. Others had only operational aspects that they were willing to offer. Jim Watson, who was still there at the time, said, I know it when I see it. But of course, that's the Supreme Court's definition now for pornography. So you can't use that for a definition of life. So I've worked up a definition of life, which people like to chuckle at. But at least I have one. And I have one from a contrived thermodynamics point of view, and I like to share it with you. And it will form the basis of other definitions of other systems, whether they be galaxies, stars, planets, life, society, and machines. They all have a similar common denominator. Here's the first part of my definition for life. Life is an open, coherent space-time structure kept far from thermodynamic equilibrium by a flow of energy through it. Dash, a carbon-based system operating in a water-based medium with higher forms metabolizing oxygen. So you note from this particular long-winded definition that the first part up to the dash is very similar to what I could describe as a star, a galaxy, a society, a city, an economy, a machine. They are all open, coherent, space-time, yeah, structures, maintained far from thermodynamic equilibrium by energy flowing through them. In this particular definition for life, it's only what comes after the dash that is peculiar to life itself, namely a carbon-based system, best we know, operating in water, as best we know, with higher forms of metabolism. My students always jump on me, value, statement, value, judgment. Who are we to say we're high? Well, higher forms do metabolize oxygen. I'm sorry, they do. So I can make an attempt for you ever so quickly to show you some of the numbers. I'm a numbers guy again. When I drive home at night from Cambridge, I'm listening to NPR, and the guy saying, he's the market guy, he's saying, let's do the numbers now. I always sit up straighter in my seat because he's going to come at me with some numbers, some quantification, some accuracy. That's the world I kind of live in. And so I'm going to share with you ever so briefly and draw you a graph. And the graph I'm going to draw you based on these numbers I'm going to share with you quickly are going to look like those curves that I showed you early on. From the earlier parts of the universe to the current, there does seem to be an increase in the amount of energy per unit time, per unit mass flowing through these various systems. So when I talk about the essence of these systems being energy, it can't just be energy and energy alone, because I know damn well there's a lot of energy flowing through a star, a lot more energy flowing through a star than there is flowing through my body. Yet I know my body is much more complex than a star. So I normalize this flow of energy by the mass, the bulk of the system involved. And I'm talking about not just, therefore, energy and not just energy flow, but energy rate density. It's a measure, a quantified measure of the amount of energy able to do work or cause change flowing through a system per unit time and per unit mass. That's all that says there. And so I'm going to just develop a table of this quantity is not a new quantity. I'm not aware of anybody who calls it by this name, energy rate density. The flow of energy through a system, a complex system per unit mass. But other people use this quantity on a regular, astronomers. Ed uses this all the time. Light to mass ratios. Physicists call it power density. Geologists call it radiant flux. Biologists call it specific metabolic rate. Engineers call it power to mass ratio. Everybody uses this term. But when the various, departmentalized, disciplinary, lingo, everybody thinks they're talking about something differently. So I'm calling it by what it is. It's energy rate density. And I build a table for you here. I'm going to list the generic system. I'm going to list the age of the system. And I'm going to list that value of that term there, which I think may be, that's my hypothesis, a complexity metric for all of these complex systems I see out the window. First up are stars and galaxies. Well, it's very simple. I won't run through the details unless you want to see them later in the discussion. But I know the ages of these systems reasonably well, and I can calculate, because these systems are relatively simple, the amount of energy flowing per unit mass through them. I can do the same for plants and animals. Plants are planets, animals coming society. But the idea here is that you see as the systems come closer to home in age, the values increase substantially. So if I were to plot this simply, I would see this kind of a plot. I don't know why I prettied it up with that fern behind there, but actually somebody else did that for me. But I'm plotting here simply the values I showed you in the previous table, energy, rate, density. And I'm plotting it as a function of time on the same scale that I showed you previously. The previous curves were hunches. They were a gut feeling that as I look out the window, things ought to be increasing in complexity. Now I'm showing you some data. I'm showing you a considerable amount of data. There's a lot of quantification, modeling, simulation, experimentation, measurement that goes into the numbers that are entering onto this. If you want a translation of this plot, it simply suggests that mature galaxies are more complex than their predecessor dwarf building blocks. Red giant stars are more complex than their main sequence counterparts. Eukaryotes are more complex than prokaryotes. Plants are more complex than protists. Animals are more complex than plants. Brains are more complex than bodies. And bodies together as a society are more complex in the aggregate than individual humans. That's what that plot says. And you can look at various parts of this plot that I've now put on a linear scale so to kind of stretch it out and expand it, and you can start looking at some of the big history milestones that move from the Milky Way through the sun, through the plants, animals, and society. But I'm putting what's amazing here, I think, and I'll stress this in a culminating slide in a few minutes, is that I'm able to put almost everything I'm seeing out the window in terms of growing complexity of all the ordered system. I'm able to put all of this analysis on one page in one graph. And so I'll just give you a rat-tat-tat razzle, quickly indicate you can look in detail at some of the interior portions of this plot, examine, for example, stars like the sun, and really look at how they move in this area here. You could look at things like plants and examine their photosynthesis. Photosynthesis is probably the most common biochemical reaction occurring on the face of the earth. People like to say that it's a highly efficient process that we don't well understand, whereas in reality it's a very inefficient process that we do understand quite well. And so you can examine in various different kinds of plants, whether they be protists, gymnosperms, angiosperms, to seafloor highly efficient plants, how in other parts of this master curve here, you can really look at the details of what's going on here in terms of rising complexity over the course of time since the Precambrian, since the Cambrian explosion. You can do it for animals as well, higher up on the curve, etc. But people want to know, everybody wants, if Teilhard were here today, he'd want to know where this curve is going. What's happening up at the top, or is there a top? That's where he thought, humankind was created in the image of God or whatever. I don't see that this plot is stopping by any means. I don't think there's any reason to suggest that this plot, that this curve will end or will reach any culmination point ever. I do suggest in that the data are showing that for physical systems in the early universe, the rate of change was sluggish. The rate of change increased with the slope of the curve increasing for biological systems rather substantially, and now the rate of change is really beginning to move rapidly, and that's because cultural evolution does move more rapidly than biological evolution, which moves more rapidly than physical evolution. But you can look in there and start looking in detail at what's going on in terms of the various quantification of the data, and you can look, for example, at humankind advancing. You can look over the course of just 1 million years, Homo sapiens moving up, increasing its complexity of various agriculturists, industrialists, technologists, and you can compare and contrast, interestingly enough, humankind advancing with machines rising, all in this topmost part of the curve. And now you see, very interestingly, that there may well be a transcendence here of some sort, whereby machines and at least their ability to do things that we may not be able to do as well or as quickly, are becoming comparable in energy rate density values than of those of humankind. I don't know what this crossing means yet. I don't know if it's significant. The data are, inaccurate. They're not precise. But you can do this I've done it for all the computers I've used in my career. I've done it for various aircraft that I've been around over my career. I've done it for a variety of various machines, and the machine-like values over the last simply 100 years are increasing as they grow more capable and more energetic and become increasingly miniaturized. I show a jet here as currently a computer-controlled jet aircraft, as current F-35 in fact, as the currently most complex system. I'm not suggesting that this has anything to do with intelligence. I'm not suggesting that energy rate density is a measure of intelligence. I am suggesting it's a measure potentially of complexity. And it's not inconceivable that a jet undergoing computer-controlled, very rapid maneuvers of a functional nature may well be considered more complex than a human being sitting, thinking in a chair. One who can show information theory would be as useful as just plain energy. But I've not been able to do it. I've tried hard. I've struck out on it. I've gotten tired of working. I've tried just trying to define information theory in terms of its various connotations. Even at that meeting, Stu Kaufman made a confession in which he felt that he was now beginning to move away from trying to explore complex systems by way of information theory and embracing more energy, because energy is something that we can define well, to everyone's satisfaction, we can measure it, its units are understandable, and we all have a rather intuitive feel for it. I don't think you can say any of that for information theory. It doesn't mean their efforts are wrong. In fact, in my gut, but I can't prove it, and I've been taken to task by a few referees recently for saying this without trying to prove it, that information may well turn out to be another kind of energy. There's a longer story behind that. But I would welcome anyone showing this same story to the degree and level of quantification that I've been able to do here, using both either entropy production or information content. Nobody has done that yet that I know of. But I acknowledge your question and I respect it. Get to work. Yes?
So in biological evolution, there is a well-known mechanism. Evolution has an arrow and it points toward increasing reproductive fitness.
Yeah.
Those who reproduce the most efficiently will crowd out those who do not. Are you proposing that there's a similar mechanism at play in the chemical and physical evolution?
First of all, you'll notice that, I assume everybody heard that question. First of all, you'll notice that in my definition for life, I didn't use the word reproduction. I didn't use it intentionally. That's because some systems that are living, I know, don't reproduce, and some systems that are not living undergo at least mechanical reproduction. So I think the word reproduction is not a strong word. And in the collection of more than 100 different definitions of life that I have accumulated over the years, only about a third of those definitions by leading biologists use the word reproduction in the definition. But I understand what you're saying, and to the extent that I can answer you now in this forum, my argument is that there's an optimal amount of energy flowing through each of these systems. And if a system is able to acquire and internalize, store, and express energy within that optimal domain for that system, then it has a chance of surviving. If it cannot, it will not. It will be non-randomly eliminated, yes. And it doesn't matter whether it's living or not. There will be, as Ernst Mayr stressed to me again and again, not only an element of chance, but an element of non-random elimination. And that will pertain not just to living systems, but a principle of natural selection, not the sense of only Darwinian selection, not just biological selection, but true natural selection extending over all of nature. Yeah. Good question, though. We're working on it. Yes?
Hi, thank you for coming.
Yeah.
So you use energy rate density as a measure of complexity. I'm just confused why you couldn't use entropy as a level of or I guess lack thereof of entropy.
Why I couldn't use lack of entropy?
Yeah.
Neg entropy.
Yeah.
Yeah. Yeah. The gentleman is asking why I couldn't use, instead of energy rate density, the negative version of entropy, which some call negentropy. If you read What is Life by Erwin Schrödinger, you've read it? The first edition and the first printing, he talks about negentropy in detail. But by the second printing of the first edition, he's dumped it. It's gone. And he explained that it was just a terribly difficult word semantically to deal with. But you can mathematically begin to explore the degree to which entropy is diminished temporarily within ordered systems. Yeah, you could do that. My problem is that when I try to confirm what I've calculated entropically with measurements in the lab, I don't know how to. I've never seen an entropy meter, like a thermometer. So I have a hard time measuring entropy. There are also different kinds of entropy, just as there are different kinds of information content. So entropy can be a very slippery term. So I understand it to a certain extent. I've worked with it, but I've put it aside. I don't have as intuitive a feel for entropy as I do for energy. I think I know how to deal with energy, and I know how to measure it, quantify it. I understand its units well, and it's that intuitive feeling. It may be old-fashioned. Paul Davies has said to me numerous times, you're just old-fashioned. You're harking back to the invention of the 19th century physicist who did, invent energy. Yeah, that's what I'm doing. It's what I understand, and I'm trying to hang my hat on that. But if you can do the same thing for negentropy, or the negative version of entropy, that would be a real contribution, especially if it confirms what I'm finding here. Other questions? Yes, sir.
All right. You talk about a new philosophy of science in the beginning, the establishment of, but this all sounds to me a lot just like Hegel's phenomenology of spirit with Geist.
With
Geist, world spirit, being replaced by probably cosmic expansion or maybe energy. And so, like, recent scholarship in philosophy has shown that his concept of history isn't necessarily especially accurate. It's because of its imminent eschatology and its rigid focus on this progression carried on by the Geist, or cosmic expansion. So, I guess more than anything,
Sounds like you're making a statement.
I'm asking a question.
Okay.
Where does this lead our place in history and in the world, I guess?
Where does this place us in history and the world?
Yes.
Well, if you could look at that arrow of time as a measure of all history, big history, then I'd like to think that this subject and the quantification we're now offering for it scientifically helps to place us into both the spatial and temporal aspects of the story. I'd like to think that this subject grants us a sense of place both in the quantification of the amount of energy flowing through our bodies and our society vis-a-vis other structures that are around us. And I'm also trying to show how that this story, this narrative, this scientific story, places us into a sense of temporal place along the arrow of time. Not that the arrow of time is meant to be anthropocentric, not that the arrow of time is meant to have a directionality, even though that big arrowhead, it kind of looks like it's pointing at something. I don't think it's pointing at anything, and I don't think it's pointing especially at us. Nor do I think there's any plan here, or purpose here, or progress here, or meaning here. I just don't see any of those things. Plan, progress, purpose, or meaning coming out of this scientific analysis. So that might leave plenty of room for philosophers such as yourself to aid us in understanding how this story could be meaningful, purposeful, predestined, etc. I just don't see that. But I'm open and I'm welcoming contributions from the philosophers. As I said at the beginning, there are many ways to understand who we are and where we came from. There's art and music and philosophy and religion and literature as well as science. But I'm a scientist, and I'm going to hang my hat on that. And that's what I've tried to do here today. But I very much respect what you're saying. Yes, yes, sir.
About the second law,
Second law, sir.
obviously.
Say again?
You talked about the second law
Yeah,
and entropy.
yeah,
And of course, entropy is not conserved, right? Energy is.
yeah.
And so entropy, according to the second law, keeps growing, right?
Well, it's not entirely clear whether a chemist asked me this a few years ago. He said, to what extent are we certain that the second law applies to the entire universe? We like to think the second law applies to objects within the universe. And there's a very definite, widespread opinion that the universe in bulk, on average, in the main, globally, is becoming increasingly disordered. Namely, the universe is dying. The whole universe is dying. But I like to, rather than stress the universe is dying, like to emphasize and concentrate and work on those systems that seem to be, that's a strong word, living. They're not all living. I'm not claiming that stars are alive or anything like that. But I'm claiming that many of these systems have phenomena similar to what Darwin and others have associated with life forms, a metabolism, an adaptability, whether it's adaptive chains or adjustments, selection. These words should not be, in my opinion, the exclusive purview of biology. These words are of a general nature and can apply to all such systems. And so those are the systems that interest me more, the ones that are temporarily in a state of dynamical steady state. They're out of equilibrium, they're not closed, they're open to energy in, wastes out, and as long as the energy comes in optimally, not too large to destroy it, not too small to starve it, but kind of just right, an optimal range of energy flow, those systems continue to survive and maintain their structure and their function for periods of time typical of those systems. So those are the systems that I prefer to study rather than the entropy of the entire universe per se. Yes?
Could you talk a little bit about what you meant when you said you were looking for laws?
Laws.
Are you
That's,
saying that you're looking for patterns in what is a complex system, or are you looking for laws that what is driving complex systems?
yeah. The question is, could I say something more about laws? That's a strong word. Maybe I even should retract that. But I am looking for a common mechanism, a common principle, a common process, some physical phenomenon that would be associated in a common unifying way with all of these systems. I mean, even when E.O. Wilson speaks of biology, he ultimately agrees, and I think he's finally put this in print because he's said this to me many, many times directly, that ultimately biology will come down to physical processes. It's not the same as saying that we are trying as physicists to reduce biology to physics. Rather, we are trying to broaden physics to include biology and all of these other wonderful complex adaptive systems and identify the common unifying mechanism or principle. Law is pretty strong. I'll take that back. I'm not sure if we have any laws. Even, Newtonian laws, Einsteinian laws, all these things will get eventually surpassed by better principles, better approximations of reality. But that's what I'm looking for, is a common, I'm a unifier, I'm a lumper. I'm not a splitter, you can see that. but I'm looking for more than just a qualified sense of what's going on. I'm looking from the point of view of a physical scientist to identify a mechanism, an underlying Platonic mechanism. Did I say that? Mechanism or principle that is common to all of these. And it seems to me to be, as best I can tell, the degree to which energy is flowing through these systems per unit time, per unit mass. That is, all of these systems have optimal ranges. They all enjoy a certain amount of energy flow through them per unit time, per unit mass. And if they are not able to acquire that in the environment they find themselves, they terminate. That's possibly, perhaps why 99 point something % of most biological species have terminated, because at some point in the history of time on the Earth, they have not been able to acquire the appropriate amount of energy, whether it be a sufficient amount of energy to avoid starvation or not too much energy to be literally destroyed. And that may also be why I proposed this at a recent meeting of the Library of Congress, why we're not hearing anything with the radio telescopes when we listen for extraterrestrial intelligence, that the principles may be so common that the majority, the far majority, maybe 99 point something % of all advanced species also eventually terminate, because they, on other planets, are not able to, as a society, as a culture, as a civilization, to control certain amounts of energy, enough to keep their cities and economies going, but not too much as to destroy them. It may be very, very hard to do that, especially as you move up this curve. It becomes trickier and trickier to survive. We are so far among the winners, but most systems are losers. Yes?
So this idea that this optimum box of energy, that I can see defines survival or not, but what drives complexity to increase?
Well, I'd like to suggest it is facilitated. Drive is a strong word. I know I used it here someplace. Yeah, it's too strong? Yeah, maybe. I'd like to think that energy itself is potentially facilitating the well-being of these systems. Energy is certainly facilitating the degree to which you maintain bodily structure. Energy is certainly facilitating the degree to which the sun continues to shine. Energy is certainly facilitating the extent to which cities continue to maintain their structure and their function. I think its energy is facilitating these systems. Maybe it's driving, I'm not sure. Ultimately, the driver, as a prime mover, it's cosmic expansion. Because we can pin that down quantitatively to about 400,000 years after the Big Bang, when symmetry broke and equilibrium of the early universe ended, and free energy, that's the kind of energy that's capable of forming, entering into change, free energy began to flow. And that's discussed at much greater length in that book that has just appeared with Cambridge Press, Complexity and the Arrow of Time, by Charlie Lineweaver in Sydney, about the ultimate driver would be the release of free energy capable of causing change and entering into complexity that was driven largely by the expansion of the universe. That's the driver, I think, cosmic expansion. Not just a facilitator. I think cosmic expansion is a driver. Excellent questions. Yes?
I noticed you had something about symbiosis.
Yeah.
So I was curious how that fit in. I'm familiar with it on the biological level.
Yeah.
I'm curious how you made dimensions.
Well, I mentioned it at the end because when I crossed those, the question had to do with symbiosis and how that fits into here. The woman is familiar with symbiosis as Lynn Margulis would have used it in biology. A wonderful friend, recently died. The way I was using it here was that when I show those curves of humankind advancing and machines rising, those curves seem to be crossing. to suggest that, as some people have suggested, that was part of what the conference in Moscow was about, Kurzweil and others, that we are on the cusp of a technological singularity that we need to fear, et cetera, et cetera. I don't see it that way at all. I see the interaction of humans and machines to be mutually beneficial to each. We see that happening every day. I mean, we're into our machines and we're utilizing machines, we're integrating with machines, I think in a reasonably positive way. It's ramping up the rate of change enormously, but I think that's a normal way in which evolution proceeds at the uppermost part of this curve. And so symbiotically, I think it's not inconceivable. I can't prove this, but I'm leaning on biological endosymbiosis ideas again to suggest that we are entering into not a transcendence of machines over humankind, it's something we have to fear, but rather a mutually beneficial symbiosis where the two of us will mutually benefit in positive ways as we go forward. Now that might mean new species. I don't know what it means for speciation. These kinds of symbiotic changes have led to dramatic changes in milestones biologically. Origin of eukaryotes, et cetera. Or you place that at 1.7 or 2.7? Lynn was always confusing on that point. But so symbiotically, again, symbiosis, I'm just leaning again on a typical word that's used prominently in biology and broadening it a bit to embrace some of these other ideas, but doing so in a rather positive way. I'm always looking for the more positive aspects of this story. I'm not trying to make this story a frightening story, an alien story, a cold and heartless story. I see this as a warm and wonderful, awesome story, but it's a story of science. It's a scientific narrative. Excellent point. Yeah, way in the back there. Yeah.
It seems like at the top of your complexity metrics, you have technological systems and society.
See, I have what? Technological?
At the top of your complexity metric, you have peaking at
No peaking.
technological systems and society.
No peaking.
No, currently peaking.
Currently maximizing. Yeah, go ahead.
In the future, assuming that we have decreasing complexity at times, will the future solely be with?
Don't know. You're asking me to predict where that curve is going. I'm not going to go there.
The question is more about possibility. Is there room for growth among biological systems that are independent from technology?
I would think, yeah, sure. Biological evolution is continuing to occur elsewhere on the surface of the planet. It's likely, I'd like to think, occurring on other planets as well. No data there yet, not a shred of evidence to support that yet, but it's hard to believe given all the space we've encountered and the number of planets that are being found, et cetera, despite the eerie silence, that there's not other species there. But sure, there's plenty of room for continued biological growth. But I'm not going to buy into trying to predict where that curve is going or making any kind of a predictive assessment. I'll share with you general trends over the next near term. But I do fundamentally think that evolution is a meandering process. It is unceasing, it's uncaring, and it is fundamentally unpredictable. And that's because the element of chance is involved all the time. I mean, Jacques Monod taught us this in the 60s with the book Chance and Necessity, right? It was a great bestseller in France. But it's not just chance either. I mean, Steve Gould used to emphasize the chance, but then Meyer would say at the same lunch, you better emphasize the back end of that natural selection process, which is non-random elimination. And the two of them together operate randomly, deterministically, chance, and necessity, but that will fundamentally make evolution unpredictable forevermore. But there's no evidence whatsoever that this curve as any measure of reasonable approximation of reality, is going to end or anytime soon. Simon Conway Morris about every month asks me, where is that curve going? I'm sure he has some agenda in mind, but where is that curve going? I have the same answer, I don't know. Other than probably upward. Faster and more complex. Your call, Lowell. A little louder?
I kept thinking about like where the trend is going.
Where the trend's going.
Right. And
So do I.
I was just thinking about it. When you measure on the y-axis, when you use units, you use energy, and so like the more energy with less mass in a way, right?
Yeah, so an object that has a certain bulk mass, if it's miniaturized, if it gets smaller, the energy rate density goes up. That's what's happening with computers. That's what's happening with jet aircraft. That's what's happening with machines. They're using more energy per unit mass.
Is it right to say that the graph is kind of exponential in the way it appears to be going?
What was the question again? Is there any? Is it exponential? If you look at it carefully, quantitatively, mathematically, it appears to be faster than exponential. Because it's going up even on a log plot. An exponential plot, a log plot would be linear, right?
It's going up like that.
It's fast.
To like predict where it's going, to find something that has really small mass, or I guess maybe no mass, but a lot of energy. That's in order to predict where we're heading for it.
Yeah, again, I'm not going to fall into that trap. I don't know how to predict this, but your sense of where the curve might be going is correct. It's larger amounts of structure and function compacted into smaller spaces, smaller masses. I mean, in the sense, for machines, it's Moore's law. And this may be underlying process that drives Moore's law. As chips become smaller and smaller. I've done this you look at some of the papers I've published for all the laptops, not laptops, starting with the UNIVAC I used as a grad student up at MIT, and going all the way up through all the machines that I've used myself. It just follows that curve quite beautifully. And it's simply because large amounts of power are being used in smaller and smaller domains. And it's driving the energy rate density up for those machines. But where it's going, I'm not sure.
Could it be like a circular?
Say again?
Can it be circular?
Circular. I don't know. The Greeks thought time would be circular. I don't see it. I see time as a linear process moving from Big Bang to humankind. I don't see any going back. I don't see any backtracking. I don't see any reversal of time. I see what you're saying, but I don't see it in the data. I see it as a linear process, but a non-directional linear process. Other than moving in the direction of greater disorder in the universe globally. That's the only direction that's suggested by this analysis.
On that, I think that I'm going to have to thank Eric Chaisson for being with us. And for
Thanks very much.